Most of you guys, all of you guys, at some point, maybe 10 years ago, maybe 10 days ago, have been on a swing set. And inevitably, when you go on a swing set, you always, at some point, try to twist that swing set as much as you can twist it so that you can let it go and spin around, right? Make sense? You know intuitively that the more you twist that swing set, the more force it requires, the harder it is to do it, right? You know that if you twist it a quarter of a turn, it requires a certain amount of force. If you turn it a half a turn, it requires more force. And if you turn it a full turn, it requires even more force. You know what we call the torsional properties, at some level at least. You know the torsional properties of the chain on that swing set. You know the twisting or the torsional properties of the chain on that swing set. You know that it requires a certain amount of force to twist it a certain amount. Well, a guy named Charles Augustin de Coulomb did an experiment that used torsional properties of a thin string to derive an equation that provides for us the relationship between electric force and the amount of charge that's present and the distance that separates two charged objects. It looks something like this. This is a simplification, but it works for us. This is the ceiling or the top of whatever that the string is hung from. This would be the string. So this would be like your swing set or the chain on your swing set. This is a little bar that has an object on the end of it. Has an object on the other end of it as well. One of those objects is charged. We'll call the one object Q1, charge 1. It doesn't really matter if the other one's charged or not. It's just there for symmetry. Now we're going to bring another object, another charged object nearby Q1. We'll call it Q2. When we do that, when we bring Q2 nearby Q1, what's going to happen? Yep. It's going to repel or attract. It depends on what these charges are, right? If they're like charges, it's going to repel. If they're opposite charges, it's going to attract. That doesn't really matter for us. Okay, it's like turning the swing set clockwise or counterclockwise. It doesn't really matter. It turns a certain amount with a certain force. It doesn't really matter which way you're turning it. So if we attract these two objects together, whatever. If we repel them, whatever. In the end, this string is going to twist. Make sense? Now, we're able to determine indirectly what the charges are here, Q1 and Q2. You understand that when Coulomb did this experiment, he wasn't able to measure the charge directly, but what he was able to do was indirectly measure the charge and therefore manipulate its value through the experiment. He was able to do that by saying, look, I got a charge on one of these objects that is Q. And then I touch it with something that's neutral and it becomes a half Q, and a half Q and a half Q. And then I touch it against something that's neutral again and it becomes a quarter Q. And I touch it against something that's neutral again and it becomes an eighth Q, and so on and so on. So he's able to not exactly know the value of the charge, but he's able to change the value of the charges by just touching them against neutral objects. So he knows kind of the relative values of the charges. He's also able to determine the distance r that separates the charges. That's pretty easy, right? Just measure. And finally, he's able to determine the force of attraction, the magnitude of the force of attraction or repulsion by how much the string twists. The string twisted this much, oh, it must have been a force of 1 Newton. If the string twisted this much, then the force must have been, it must have been 1.7 newtons. If it twisted that much, it must have been, 2.3 newtons, or whatever the case may be. So he's able to determine Q1, Q2 indirectly. He's able to measure directly R, and he's able to determine what the force is in newtons by simply looking at how much the string twists. Okay? Now, what does he do with this? So he performs 3 basic experiments. Okay? In the first experiment, he would manipulate the value of Q1, and he would see how force responded to that. So he manipulates Q1, and he sees how force would respond to that. What would be my control variables, by the way? If I manipulate Q1, and F responds to that, then what do I got to keep constant through this? What's one thing that I got to keep constant through this? Q2, good. What's another thing that I got to keep constant through it? Good. Q2 and R, the distance that separates them. Good. Make sense? Like, when we do a lab, and we're going to do a simulation on this in the next couple of days here, any lab we do, I always tell you the control variables that I'm concerned about, the ones that I really care about, are the really important ones. What else you got to keep constant? The humidity in the air, the temperature in the air, whatever, yeah? Like those, sure, they're important, but what are the really important ones? Well, if we don't keep Q2 constant and we don't keep the distance constant, then we're not going to find a relationship between Q1 and F, right? All right, so what is he going to do? Well, he plots a graph of F versus Q1. And when he does that, he gets this shape. He gets a straight line. So he manipulates Q1, F responds to that, keeps Q2 and R constant, gets a straight line graph. That tells him that we have a linear relationship. In other words, F is directly related to Q1. I know you guys haven't seen this symbol in math, which always surprises me. That's a proportionality symbol. It means as something happens to Q1, the same thing happens to F. As Q1 goes up, F goes up. If Q1 goes down, F goes down. If Q1 is tripled, then F is tripled. Make sense? All right, there's the first little experiment that gave Coulomb the relationship between F and Q1. Now he performs another experiment. This time, he's going to manipulate Q2 and see how F responds to that. What would be my control variables this time? I'm changing Q2, so clearly that's not going to be a control variable. Taylor, what's going to be one of my control variables this time? R, yeah, the distance that separates them. Be careful with the wording of that radius. Okay, you're the second person who said that. It's not really a radius because you're not going in a circle, right? It's just a distance that separates them. It's just a symbol R that kind of looks like radius. What else do I got to keep constant? One more thing that's really important to keep constant here. Jaden? Q1, yeah. If I'm manipulating Q2, then I got to keep Q1 constant. I'm going to plot that graph, F versus Q2, and that's going to be a straight line graph as well, which tells Coulomb that F is directly related to Q2 as well. So in other words, as Q2 goes up, F goes up. If Q2 is decreased by a factor of 13, then F is decreased by a factor of 13. They're directly proportional to each other. Finally, the third and final experiment that he performs, he manipulates the value of R and sees how F responds to that. So he changes R from one trial to the next, sees how F responds to that. What would be my control variables in this case? What do I got to keep constant this time? Yep. Q1 and Q2. Can't change the value of Q1 and Q2 in this experiment. Remember, if you have more than one manipulated variable and you see an effect in the fourth, well, you don't know what caused it, right? That's why you only got to have one. Now, when he plots this graph, a little bit uglier, this graph ends up looking like this. And that could actually be a couple of different relationships. It could be a couple of different relationships. The graph looks remarkably similar for a couple of different relationships. But in this case, it works out to be an inverse square relationship. So it looks like this. As R goes up, F goes down. In fact, F goes down faster because it's a squared relationship. F is inversely related to 1 over R squared. So he does three little experiments with this. The first one manipulating Q1, the second one manipulating Q2, and the third one manipulating R. And he gets three different relationships with this. But then he's got to put them together. He doesn't want three different relationships. He wants one relationship to relate everything to the force. Everything at the same time to the force. He said F is related to Q1. He said F is related to Q2. He said F is related to 1 over R squared. So when he combined them, he said F is equal to, well, actually, let's say it's related to Q1 and Q2, both on the top because they're both linear relationships. Q1, Q2 over R squared because it's a inverse, we call it an inverse square relationship with R squared on the bottom. Now that's not equal, it's related to this. As this term doubles, F doubles, as this term goes down by a factor of 7, then F goes down by a factor of 7. To make it equal, to make it an equation, we have to add a constant. If I was looking at a graph, y is related to x, then I would replace it with a constant called m. M would stand for the slope, right? Okay, in this, I replace it with a constant k. K has a value of, as it turns out, 8.99 times 10 to the 9 coulombs times meters squared. No, it's not coulombs. Newtons times meters squared per coulombs squared. If you ever forget the units for that, don't worry about it. It's on your data sheet. The number is on your data sheet, as are the units on your data sheet. So now we're saying the force between two charges a certain distance apart will be K, which is that constant, times the value of the first charge in coulombs, by the way. We often see it in microcoulombs. You'd have to convert it to coulombs here, times Q2, also in coulombs, divided by R squared, R being the distance that separates them, measured in meters. Make sense? Does that equation look a little bit familiar to you? You ever seen that before, or something like that before? What is it like? Yeah, it's kind of like slope there, yeah. In fact, we can relate this to a graph. We will in that little activity, that simulation activity that you're going to do. Think of physics 20, yeah? Yeah, gravity. Remember, with gravity, this is, here, let me just write it. This is Coulomb's law. But we had one for gravity that looked an awful lot like that. It was F is equal to G times M1 times M2 over R squared. We know there is a remarkably similar relationship between gravity and electricity in terms of that force, and in terms of a lot of other things as well. We don't actually know why. We don't actually know why the relationships are the same. But we figure there's got to be a reason. There's got to be some way to tie it all together. We just haven't figured out to this point in 2019 what that reason is. Okay, in the end, the equations are remarkably similar. We call them both inverse square relationships because the force is inversely related to the square of the distance in both cases. This is called, by the way, Newton's law of gravitation. You guys, anybody remember the constant there? Big G? Not 9.81, that's little g. The big G? It's probably on your data sheet. I think it is. Yeah, big G is 6.67 times 10 to the negative 11. And this is not Newton meter squared per Coulomb squared. This is Newton meter squared per kilograms squared. So it's a different equation, right? It's a different constant. We're talking about M1 and M2 rather than Q1 and Q2, but clearly there's something there, right? Some relationship there because the structure of the equation is identical. And it's going to happen a few times through this unit where we're going to notice a lot of similarities between electricity and gravity. Now this table you see here is just a little summary of it. of these two laws. Coulomb's law, which is the one that we just learned, F is equal to K, Q1, Q2 over R squared, and Newton's gravitation law, which is F is equal to big G, M1, M2 over R squared. You can see that in both cases, the relationship is an inverse square relationship. That simply means that F is inversely related to the square of the distance. As R goes up, F goes down. The further you get away from each other, the weaker the force gets. That should make sense, right? If you get further away from the Earth, the force of gravity between you and the Earth is smaller. If two charges get further away from each other, then the force gets smaller. Now, the magnitude is a little bit tricky. We typically think of as gravity as being a big force, right? If you step off of a ledge, you fall. And we know that, and that scares us, right? That's what makes us afraid of heights. Some of us, at least, afraid of heights, is because we know that if we step off, we're going to fall. Gravity is a big force, right? But in the grand scheme of things, it isn't actually. There's four fundamental forces. There's force of gravity. There's an electromagnetic force. There's a strong nuclear force, which we already talked about. And then there's another one that's called the weak nuclear force that we don't really get into in Physics 30. Gravity is actually the weakest of the four. Of the four fundamental forces, gravity is the weakest of the four. The electric force is stronger than the gravitational force. You know how we remember that? We remember that because the constant for gravity is 10 to the minus 11, and the constant for electricity is 10 to the positive 9. So all other things being equal, that constant will make the electric force quite a bit bigger than the gravitational force, right? Finally, the last thing we're going to do to compare here is the direction. Gravity is always attractive, right? There is no gravity that pushes two things apart from one another. You've got mass, there is a minuscule force of gravity pulling you guys towards each other. You'll never notice it because your masses are so small, but it's there. And it's always an attractive force, never a repulsive force. Whereas if you were a charge and you were a charge, hey, one of you could be positive, the other could be negative, where you'd attract, or you could be both positive or both negative, where you would repel. So Coulomb's law can be attractive or repulsive, and Newton's law of universal gravitation is only attractive. Make sense? Good? All right.